It's science, but not as you know it. The Naked Scientists.
Hello and welcome to this week's Naked Scientists with Chris Smith.
Hello.
Dave Ansell.
Hi there.
And I'm Dr. Kat Arney. And in this week's programme, we have the robot equivalent of Spider-Man, a new invention that could see robots running up walls using electricity to stick on. Also, we've discovered how scientists have uncovered the basis of how good gut bugs could make us healthier. And we've got some fresh insights into prostate cancer and how hormones can play a key role in the disease. And that's all on the way. Chris.
Thank you very much, Kat. Now, this week it's our science phone-in extravaganza, so we're going to be taking your science questions and hopefully answering them for you. We've so far heard from Steve. He wants to know, would you bleed blue blood into a vacuum? Answer to that one coming up shortly. Also, Fran wants to know why things seem to shimmer in the distance on a hot day. And Zach says, what would happen if two planets collided? So the answers to all of those are on the way. Plus, we're going to be hearing how the internet is now giving the aviation industry a run for its money when it comes to global warming.
We're looking at probably 2.5, 3 megawatts of heat being rejected from this roof at the moment.
To give a sense of how much heat that is, if that were turned into electrical energy, that would be enough to power 1,000 homes.
Pretty much exactly right, yes.
So it sounds like a very hot story. We'll also have the latest on how the Phoenix mission is getting on with its analysis on the surface of Mars. That's coming up. Dave.
Thanks, Chris. And in this week's Kitchen Science, I'll be showing you how to create a very unusual and beautiful effect. You'll need some milk, some food colouring and some detergent. Instructions on how to do it, they're on the way.
That sounds fab. So if you've got a question for us, and the wackier the better, I don't know why I'm saying that, we could get into trouble, do get in touch. Email chris@thenakedscientists.com.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Well, let's take a look at what's been happening around the world in science this week. And Dave, Spider-Man, always a favourite of mine, but now it could become a reality.
Well, not necessarily with people, but certainly with robots. Now, robots are becoming more and more important in war zones, disaster areas and everyday life. They're often used to get at places which people can't access either easily or safely. At the moment, ground-based robots are basically constrained to fairly flat surfaces on the ground, and flying robots, they can get just about anywhere, but they use a lot of power and are kind of hard to control. Now, one way of getting around this is to climb up walls, and various groups have tried to make wall-climbing robots based on suction pads, like that Spider-Man guy who used to do that in the 70s, or reusable gecko adhesive. But none of them work very well if the surface is dusty or dirty. Now, researchers from SRI International have invented a really elegant way to make robots climb walls. It uses the same principle as how you can stick a rubber balloon on your hair and then stick it to a wall. This process is called electroadhesion. The balloon sticks because when you rub it, you build up a large negative charge, and when you put it near the wall, the part of the wall close to the balloon becomes positively charged. It attracts the balloon, and this attraction is large enough to cause friction to hold it up. But on a conducting wall, of course, then the all the charge will escape from the balloon and the balloon will fall off.
So how have they got around that?
Well, Harsh Prahlad and colleagues built a robot on a very similar principle. They've basically got a load of electrodes with a very thin layer on a rubber sheet, with a very thin layer of insulating rubber beside them. You charge those electrodes up to thousands of volts, put them very close to a wall, then the same way as a balloon sticks to things, and it'll stick to the wall.
Oh, right, so the charges on the electrodes, this is prevented from getting into the wall by the rubber, which is between the electrodes and the wall, but because the rubber becomes charged, it behaves a bit like a balloon that's been rubbed on your head.
Yeah, and because the rubber's flexible, it can get very, very close to the wall, and it sticks well.
So how does the robot move along? Because it's all very well to stick it on, but then how does it get mobile? Well,
what they've designed is they've basically got a track, and they've got lots of little flaps on it, which is made out of these rubber pads, and then the pads stick onto the wall, and then as the track moves down the wall, then they stay stuck. And then when they should be released, they just turn off the voltage, they stop sticking to the wall, and then it can pull off, and then the track can go back up.
Quick question, electricity and water don't mix. Will this work in the wet?
That is their one problem at the moment. They can support between 20 and 140 grams per square centimetre on a dry wall, dusty wall, absolutely fine, but if it gets wet, it tends to stick to the water better than the wall.
Any way around that?
They're working on it, but I haven't heard of how they're going to get around it.
So not an underwater robot then. Right, well, this is an interesting story because last week or a week before last, we talked about bacteria in the human body and how we're, in effect, passengers in our own body because we're outnumbered both on and in us by bacteria. There's about 50 times more bacterial cells than there are human cells in the average human. And we know that people who are prevented from having the right sorts of bacteria on their bodies are less healthy. So a group of researchers led by Sarkis Masmanian, got a paper in this week's Nature, he's at Caltech, decided to explore this a bit further and find out how bacteria can make us healthier. They had a particular group of mice in which they were reared without any opportunities to pick up bacteria from the environment. So these were sterile mice, if you like. And they then infected them with a kind of bacterium called Helicobacter hepaticus. And these mice developed ulceration and inflammation in their gastrointestinal tract. The researchers found, though, that if they gave them a dose of another bacterium called Bacteroides fragilis, which is a common good bacterium found in us and in other animals, they could prevent this inflammation occurring. And that suggested to them that in some way these other bacteria were warding off some of these dangerous effects. To find out what was going on, they then found that the good bacteria were in some way suppressing the levels of hormones, including one called IL-17, which triggers the immune system to go into inflammation. And they also found that they were encouraging the production of T cells called regulatory T cells that seem to switch off the immune system. So how are they doing that? Well, they seem to produce a chemical called PSA, which is polysaccharide A. This is a group of sugars that come out of the bacteria. And they know it's those sugars because when they gave the mice just that sugar solution and the bad bacteria, they didn't get any inflammation. And when they removed the gene from the bacteria that make it and put the bacteria in, the mice still got the inflammation. So it proves it's this PSA molecule. And now they need to know whether, intriguingly, you can use this to treat things like Crohn's disease or ulcerative colitis, because these are human conditions where people suspect that it might be because you've got the wrong spectrum of bacteria in you and on you, and that's what's driving some of the inflammation. So the big question now is, if you give people some of this PSA, will it make their inflammation better?
Well, I have to see how long it is before it turns up in some probiotic yoghurt drink on the telly. Maybe it's in there already, who knows? Anyway, this is a story about prostate cancer, which is a disease which affects more than 670,000 men across the world. And now researchers have known for a long time that prostate cancer is fueled by the male sex hormone testosterone. And often men with prostate cancer are given drugs that block the production or the action of testosterone in the body. And usually these treatments are pretty successful, but they do stop working after a while because the cancer develops resistance and starts growing again. But now scientists in America have made a very surprising discovery that could actually have a potentially really big impact on the way that men are treated. Now, led by Dr. Mark Rubin, the scientists analysed the activity levels of more than 6,000 genes in 455 samples of men from men with prostate cancer. So these are prostate cancer samples. And they found that samples from particularly aggressive cancers were actually being driven by the female hormone estrogen. Now, men do produce some estrogen in their body, so it's not, really weird. But to get a little bit more detailed, around half of all aggressive prostate cancers are driven by something called a fusion protein. And this is created when two really important genes for driving cells to multiply get stuck together. And they actually found that estrogen was really fueling this fusion protein, making the cancer cells grow. But what does this actually mean for men with prostate cancer? Well, we know for a start that estrogen plays a really important role in breast cancer, and there's lots and lots of very successful drugs for breast cancer that target estrogen. So perhaps we could use these drugs, perhaps we could use similar drugs.
Has no one tried that? I'm quite surprised because
there's been some. I think some female drugs are used, but this is the first time they've actually found that it's the receptor for estrogen that's really driving this aggressive form.
Testosterone encourages it, and men get given drugs to stop them making testosterone, and that makes their prostate cancer slow down or shrink. So this is interesting that the other female hormone does similar thing.
It's a very new discovery. It's very interesting. And then on a slightly more speculative note, there's maybe a possibility. There's been some talk about estrogens in our environment or estrogen mimics in our environment possibly leading to some cases of breast cancer or that kind of thing. And maybe that's being responsible for fueling some prostate cancers. But that's really very speculative at the moment. It's a really new discovery.
Okay, cool. Now, back to the subject of robots. Now, orbiters now we're talking about robots on other planets and how footballs could be the answer to how to explore them more efficiently. Now, we've got brilliant orbiters that go around Mars. They give a brilliant view of the whole surface. You've even got pictures where each pixel's down to like 25 centimetres. And but sometimes you've actually got to go down to the surface and have a look much closer. And last week, for example, the Phoenix lander touched down, and we'll be digging holes, and we're finding out more about that later on in the show. But it can only look in one place, and rovers like Spirit and Opportunity can travel further, but in 4 years they've only travelled a few kilometres, which isn't very far on something as big as a planet. Now, researchers from Angstrom Aerospace in Sweden may have a solution to this problem. The design involves putting the rover in what's basically a football, about 30 centimetres across. You can then put an axle across the inside of it and then put all the electronics and batteries on a sort of pendulum on the bottom. You can move this pendulum and make it move forwards. And by keep moving the pendulum forwards, it will keep rolling and rolling and rolling.
Didn't the Victorians have something similar for humans to ride around in as a joke? It was a sort of ball that you sat inside and you could wander around a bit like a hamster ball, but you sat on this seat that was the axle in the middle. So you stayed upright, but the ball moved. Not practical, but fun.
Yeah, that's basically exactly the same idea. So then you've got this axle, you'd have to put the cameras on the end of the axle because it's the only bit on the outside which stays still.
Where would you put the solar panels? On the same sort of thing?
Their idea is to use flexible solar panels on the outside. So
it's a giant solar panel ball, if you like. Ingenious.
And because it's inflatable, it will take up much less space than equivalent rover.
Why has no one thought of this before? It sounds really, really obvious.
It's probably just difficult to do, and they're very, very conservative when building rovers. So they've built ball robots before, but not non-inflatable ones. It takes about half the space. And because it's a football, you don't really mind it bashing into things because it's a football. So they reckon it could do about 30 kilometres an hour and do about 100 kilometres on a charge, which is hugely better than robots up till now.
It's amazing, speedy. We're talking of robots. There's a very interesting discovery which was announced this week by Andrew Schwartz and his team in the journal Nature from the University of Pittsburgh, this comes from. And what they've done is to develop a way in which you can control a robot just using the power of brainwaves. This technique involves developing an electrode which can be implanted into the brain's motor area, and this electrode has lots of tiny miniature electrodes inside the main electrode, and effectively it can eavesdrop on the electrical chatter that goes on between nerve cells. Now, if you look at how the brain encodes movements, the brain has on its surface a map of the human body, and there are different cells representing different bits of the body in different places around the surface of the brain. So if you put your electrode into the part of the brain that controls the hand, for example, the nerve cells there will principally be talking about hand movements. What this team have managed to do is to write computer programs that can decode how those cells talk to each other when they're going to make a movement, and then translate those movements into the movements of a robot. So a monkey can be shown a piece of food in front of it, and it can, by just thinking about it, reach out with the robot arm, take hold of the piece of food, and then bring it back to its mouth and feed itself. And because it's so specific and precise at recording just from the clutch of cells that is involved in hand movements, the monkey can move its head around, its eyes around, and it won't interfere with the signal that they're picking up. Now, what we understand about how the brain controls movements is if I asked you to imagine you were standing looking at a giant clock face and you were going to reach out and say touch the number 2, then what would happen is this would involve a movement out away from your body, upwards quite a bit, and to the right a little bit. So, in other words, there will be a cell in your brain that would say, I principally want to move right, so that would be activated a little bit. There'd be another cell which involves arm movements upwards, so that would be activated quite a lot. And then another cell which would be activated a lot to move your arm away from your body. So by adding together the relative contributions of each of these cells, that's how you get the final direction and speed and range of movement of what the brain wants you to do. And it's eavesdropping on that. That's what the team have done. And why they think is important is that we could effectively take people who've had strokes and can't actually get the rest of their body to move and wire those signals into the rest of their body. Or you could take people who are, say, amputees, and rather than giving them a rather blunt prosthesis that they can only control with fairly rough movements, you could actually, with the power of thought, enable you to move that fairly accurately. And this is much better than the present designs we've had so far, where they've really been limited to people moving a cursor around on a screen. So it's a big step forward.
I'd be slightly worried about if I had one of those, I'd just end up in the shoe shop all the time. I didn't know, your real intentions underneath. Anyway, ever since Prince Charles's infamous grey goo speech about nanotechnology, there's been lots of worries about the safety of nanoparticles in the environment. And adding fuel to this fire, last week researchers in Edinburgh published results in the journal Nature Nanotechnology showing that carbon nanotubes of a certain length could actually cause damage to the lungs, similar to the effects of asbestos. So this is all very worrying, lots of stories about it. Are we all going to die? But not all nanoparticles are the same. And writing in the same journal in Nature Nanotechnology, some scientists from the US National Institute of Standards and Technology have been studying whether fluorescent particles called quantum dots can actually build up in the food chain. Now, we use quantum dots for applications such as medical diagnostics and potentially treatments.
You take a quantum dot, you go on a quantum trip.
Quite possibly. But we really need to know if these things can build up in the food chain, because obviously pollutants do tend to build up in predators the higher up you go up the food chain and can be quite poisonous, so that's bad. Anyway, the scientists have used quite a simple food chain to start with. They've just used two little aquatic organisms, a predator species and its little single-celled prey, and they found that the prey could take up the quantum dots, and they were passed on to the predators when they ate them, but the amount transferred was really quite low and the dots didn't really appear to build up that much. So these are still very early results. It's only a couple of things in the lab, but it is a promising sign that at least some types of nanoparticles might not be quite as bad as Prince Charles would have us believe.
Let's hope not, because of course there is obviously a lot that we can get from nanotechnology, but we may also have a lot to lose if it goes wrong. Thank you, Kat. This is The Naked Scientist with Chris, Dave and Kat Arney, and if you'd like to ask us any questions, it's our science Q&A, our science phone-in extravaganza. Email chris@thenakedscientist.com. Coming up, Penny wants to know about bees.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
So Penny, bees. What can we do for you about bees?
Well, hi. We've all heard the expression, haven't we? Bees, it's like the bee's knees. So what I'd like to know is, do bees really have knees?
This is a really good question. And in fact, they kind of do. Bees do have segmented legs. They have parts called a coxa, a trochanter, a femur, a tibia and a tarsus. And this does equate to bits of their legs. So technically they do have knees. We're thinking maybe, there's been some discussion on the Naked Scientist forum about this, and Turnip Sock suggests that perhaps the expressions come from the fact that they store pollen in these hairy baskets on their knees. They have like hairs on their knees, and you get big build-up of pollen on the knees. So maybe that does look like, something big and spectacular full of pollen. So that could be where the expressions come from. Not really sure. But yes, bees do have segmented legs, and so they do have what could be described as knees.
Oh, great.
There you go.
Good to have you with us, Penny. It's a good question. It's because it just gets trotted out every day, the bee's knees, and no one ever really thinks about why.
That's right.
Thank you ever so much.
Thank you.
Good to have you with us.
Okay, bye.
It is The Naked Scientist with Chris, Kat and Dave. And coming up, we're going to be hearing shortly why the internet is becoming a worse polluter than the airline industry, and also finding out about a computer program that's come up with a new way to get rid of mosquitoes.
But first, Dave is going to do some very impressive-looking kitchen science live in the studio. Is this going to work, Dave?
Just before you start, I have to say that Mark in Bletchley has dropped us a line to say the last time I did kitchen science I made a huge mess, so this time I think I will just sit back and listen.
More mess. This looks messy.
This shouldn't produce too much mess, and it's really, really beautiful. So if you're going to do any one, I'd do this one. It's lovely. Now, for this experiment, what you need is some milk, sort of maybe about a quarter of a pint of milk, a fairly flat bowl.
Does it have to be any type of milk? You've got whole milk there.
It should work with any type of milk.
Okay.
I think it affects it slightly, but it should work with all types. A couple of colours of food colouring. So I've got some green, some blue, some red.
Ooh. So this looks messy.
And some washing up liquid. So what you do is you pour about 1 centimetre of milk into the bottom of your bowl, which I'll do now.
This is full fat milk. It's not a very healthy experiment, Dave.
They didn't have anything else in the shop.
Does it matter? Does it matter if it's skimmed?
It shouldn't matter too much. It'll affect it a bit, but it should have a good effect, whatever kind of milk you have. So pour about 1 centimetre of milk in the bottom.
Okay, nice healthy slug of milk.
And then, I'm not going to do it now because it will go off during the show, but then pour a little bit of food colouring into 2 or 3 places, different colours and different places on the milk. And then take a drop of washing up liquid and drop it into the milk and see what happens.
Does it matter where in the milk you put the washing up liquid?
It doesn't really matter. And then wait for a couple of minutes and see what happens. If you get bored, put some more
And
washing
what do you
up
want
liquid
people to tell you?
Phone in and tell us what it looks like, what weird effects you can see on the milk.
That sounds fantastic. So it's milk in the bowl, drop some food colouring on the top of the milk, drop a washing up liquid in the middle. What on earth happens? Yes. So if you've done that at home and not made too much mess, do give us a call and tell us all about it. And also, if you've got any Q&A for us today, we are answering all your weird and wacky and wonderful scientific questions. So come on, throw them at us. You can email chris@thenakedscientists.com.
Now, last week on The Naked Scientists, we were talking about the NASA Phoenix mission, and that was due to land just a couple of hours after the show was going out. And that was all about trying to understand a bit more about what the surface of Mars was like in the past. Well, fortunately, Phoenix did land safely last week, which was much to the relief of William Boynton, who was on the programme. He's actually part of that mission. He designed something called the Thermal and Evolved Gas Experiment, which is analysing the Martian soil. And he's from the University of Arizona, and he's with us again this week to give us an update. Hello, William.
Hello there.
Thank you for joining us again this week on The Naked Scientist. We thought we'd catch up with you to find out, now we've established that Phoenix has landed safely, what it is that you'll now be doing over the next few months to understand more about the surface of Mars.
Okay, yes, well, first of all, we're incredibly excited that we finally got there. That was really kind of a hairy time when we're not sure everything's going to work, but we did eventually get down to the ground, and that's good. This last week, we've been going through what's called a characterization phase, where we're really trying to just look around us and take some pictures and sort of map out the landscape so we know what we're working with. It's going to be about another 3 or 4 days before we get down to actually collecting samples and doing the analyses of them with the various analytical instruments that are brought on board.
What sorts of experiments will you do?
Well, the instrument that I'm responsible for, as you mentioned, we call it TIGA. It will take some of the soil and ice samples that are dug up by the robotic arm, and it puts them into a very tiny oven. We heat the samples up in the oven, and there's 2 things we're looking for. If there are any phase transitions, this is where, for example, if we have ice, when we heat it up to 0 Celsius, it will melt. It takes more heat to do that, and so we are keeping track of the heat required to raise the sample. That way we can tell how much ice is in the oven. The other thing we're doing is we're looking at the gases that are given off by the sample as we heat it. We pass this gas on to the Evolve gas analyzer, which has a mass spectrometer in it that tells us what gases are given off. And so if we see water come off at a certain temperature, that can tell us the nature of the mineral that evolved the water.
So what are the big questions that you'll be answering with these experiments?
Well, with that particular one, we'll just be looking to see how much ice is present mixed in with the soil. We actually think it's very high ice content once we get beneath the soil. We'll be looking for isotopic ratios. This is for the same element, 2 different nuclides that have different masses, and the most important one is for hydrogen. Normally it's mass 1, but there's another form of it called deuterium, which has mass 2, and the ratio of those 2 things can tell us something about the history of the water and the temperature at which the ice formed in the past, things like that. We do have one other part of it that we're very hopeful will get some interesting results, and we will be looking for organic compounds that might be evolved from the sample as we heat it up to high temperatures.
Cool. What does Mars look like where you've landed?
Actually, perhaps somewhat surprisingly, it looks pretty much as we expected. It's kind of interesting. Before all of these missions actually land, there's usually some artist concept of what the lander is going to look like on the surface and things that are passed around to the press and so forth. And this time it was actually quite remarkable that the artist concept agrees pretty much with what we see. We see a very, very flat region, very little topography. But we're also on this area what's called pattern ground or polygonal terrain. And what we find is that we land in this area which is filled with these polygons that range in size from a few meters on up to really quite large ones. And this is due to cracking of the ice. During the very cold winters on Mars, the ice will contract and shrink, and it leaves cracks. And then in the summertime, it expands, and the ice expands back to fill the cracks, but meanwhile some dirt is falling into the cracks. And so it ends up, after many, many years of this, we end up with these polygons which are formed by these cracks.
Well, looking at how you're managing to survive on Earth at the moment, William, I understand that you're living on Mars time. How does that work?
Yes, it turns out this lander is powered by solar cells, and so it's only in the middle of the day, actually maybe from about 9 a.m. to 5 p.m. local time on Mars, that we have enough sunlight to efficiently operate the lander. Now, we're in the high latitudes in the North Pole in summer, so there's sunlight shining on the lander all the time, but really not enough to power it. So the lander goes to sleep every day about 6 p.m. local time, and it'll wake up the next morning about 8 or 9 a.m. local time. And turns out Mars day is about 40 minutes longer than an Earth day. And so we can only operate that on this 24-hour and 40-minute cycle.
So your days are getting 40 minutes longer every day?
Yeah, our days are getting 40 minutes longer every day because we have to be there when the lander goes to bed and sends down the data for us to look at.
You have my sympathy. I'm sure your body clock is now totally screwed.
It is really messed up. It's like perpetual jet lag, 40 minutes more every day.
Good luck with that, William.
Oh, thank you very much.
Thanks for joining us on The Naked Scientist. That was William Boynton, and he's from the University of Arizona, and he's part of the Phoenix mission to Mars. So thank you very much to him.
Laying the facts bare, The Naked Scientists.
It is The Naked Scientists with Chris Smith, Kat Arney, and with Dave Ansell. Now, don't forget, we've also got Question of the Week, and this week Diana O'Carroll will be finding out how a didgeridoo works. But first, Dave, this question from Zach, since we're talking about science. He says, what would happen if two planets collided?
Well, start off with something a bit smaller. Now, when the impact which we think wiped out the dinosaurs, that was when about a 10 to 15 kilometre asteroid is thought to have hit somewhere in Mexico in Chicxulub. And that, just a 10 to 15 kilometre asteroid hitting the Earth released energy equivalent to about 100 million tonnes of dynamite exploding, or TNT exploding. And just to compare to that, the biggest nuclear bomb we've ever built is equivalent to 50 million tonnes of TNT. So this is an immense amount of energy. Now, if you scale that up to something the size of a planet, so several thousand kilometres across, the amount of energy released is going to be absolutely immense. Now, we think that actually Earth was hit by, or what we call sort of proto-Earth, which is called Theia, was hit by another object about the size of Mars about 4.5 billion years ago. And when this hit the Earth, it collided and it's released an absolutely immense amount of energy. It completely melted everything in the Earth. The two cores of the core of the planet which hit the Earth went straight in and ended up coalescing with the core of the Earth. And then there was a load of stuff thrown out. An immense amount of, like, the lighter rocks on the surface, immense amount thrown out. You got lots of particles. And these coalesced into a ring and then coalesced into the moon. So the moon's made up of much lighter rocks than the Earth. And the Earth is denser than it ought to be because it's just the two cores. So
the bottom line is, if you have a planetary collision, it's messy, but it can give rise to whole new worlds, in this case the moon. Now, Kat, here's an interesting question. Tad Davison says, do hairs lose their pigment when you go grey, or do the coloured ones fall out and they get replaced by the grey ones?
Very pertinent. I've been finding my first grey hairs. This terrible, terrible thing. Anyway,
what about on your head?
Yeah, yes, on my head. Yes. You can't see them anymore. Anyway, the first thing to note is that grey hairs are actually not grey. They're white, because your hair colour is determined by pigment that's made in your hair follicle cells, and kind of it goes into the hair. So it comes a time in everyone's life where basically the pigments stops being produced, and so you start producing hairs that have no pigment, so they're white, and this mixed with your hair colour gives the grey effect. Basically, I don't think from looking at it that you get a hair that starts off brown and then becomes white. You tend to get hairs that start off being white. Another question is, do people's hair really go grey overnight? And I have looked at it a bit, and there seems to be a bit of an argument in it, and the only way I can see it's possible is if someone has very short hair, and they go grey due to some sort of stress event and maybe some of their hair's falling out. It might look like over quite a short period of time, if you have very short hair, you appear to be going grey very quickly.
Because you can find hairs, because I've seen patients who have a hair which they've then showed me themselves and said, this is interesting, Doc, look at this, and it's white at the base but then brown halfway along, where it's literally run out of melanin to add to the hair and it's changed colour.
Yeah, that would probably be under that sort of medical circumstance.
Now, Steve's in his car. Hello, Steve.
Hello.
Thank you for joining us on The Naked Scientist. What can we do for you?
Right. If you're driving up, the example I did, driving along motorway, get a lorry next to you, the front wheel of a lorry, the nuts are sticking out, and as it's driving along, it looks like it's a ring because it's going so fast. But if you really burp, the nuts then stop whilst you're burping, and then once you've burped, they start revolving again.
I have to say, this is a fantastic question. You can achieve the same effect, not with necessarily an upthrust of wind, but also by crunching your cereal. If you were to go along in a car and eat some cereal at the same time, you can see this. And also, if you've got an LCD clock, if you've got a clock radio or something at home, you can also get the same effect, Steve, with that. If you look at a clock radio and eat something at the same time, you'll see the numbers appearing to jump or flicker on and off. And what's happening is you're creating your own in-body stroboscopic effect. The vibrations when you are eating are being transmitted to your eyeballs, and they're making your eyeballs move very slightly, and the rapid movement of your eyeballs is capturing the movement of just the right way of those nuts going round on that wheel, or, in the case of the LCD clock, the light flickering on and off. And that's why it appears to jump all of a sudden, or freeze and be off for a fraction of a second. So it's literally your eyes moving together in uniform, very quick, very unison, because you're crunching or burping or making a movement which jolts your eyeballs a little bit in your head. So that's the reason why you see that.
Right. Can I ask another question?
Go on then.
In two parts, vampire, a person, not bats or anything else, could someone just live off blood? And in the film Soylent Green, they sort of dry people out, make tablets, and other people eat them. Is that feasible?
When they dry the person out, what do you mean? They take a whole person and just desiccate them?
Yes, I think in the film Soylent Green, that's what they did. The people that were dying, they were then making it into food pellets for people to eat.
Yes. Well, in theory, you could do that. Blood is actually full of protein, and it's full of iron. And iron's something you need in your diet. You do need iron, so blood is good. Black pudding is just congealed blood that you fry. Blood also contains water, which you need, and some salts in there, so you can get protein, salt and iron from drinking blood. There will be other things that you can't get from blood, like water-soluble vitamins, which are not present in very large amounts. There will be fat-soluble vitamins as well you won't get in very large amounts from blood. So I think you could probably make a reasonable meal out of blood, but it wouldn't make up for all of your dietary requirements. And so you might want to eat some freeze-dried body pellets, which would sort of supplement your intake. That's no different, really, from eating a microwave meal, which is effectively just a dried-out bit of body. It may not be human, it's just animal instead. So I think actually it could work, yeah.
OK, well, thanks very much.
That's all right. Thanks for joining us on the programme.
Bye.
OK, quick one for you, Kat, and Peter Williams. And he says, is the moon visible? Why is it that the moon is sometimes visible during the day?
Well, we've gone to the forum for this one, and basically it's visible because, you know, when it's in the sky, it's just another object being lit by the sun. So when it's in the right place, we can see it. Those are my kind of ignorant answers. Someone also says, Liner has said maybe it's a cheese in flight. And it has progressed on the forum to a very big argument. So maybe, Dave, you can tell us a bit more about the moon.
Yeah, the moon is orbiting the Earth once every 28-ish days. And if it's between... you can't see it during the day if it's right between us and the sun, because you see the back of it, which isn't lit up by the sun, so it's very dark, so you can't see it. But if it's sort of at 45 degrees off the sun, or even 90 degrees off the sun, between the sun and the Earth, then half of it will be lit up really quite brightly. And then the surface of the moon is about as bright as the surface of the Earth is, so there's no reason why you shouldn't be able to see it. And so as long as the moon is at sort of 45 degrees, the moon's on the sunward side of the Earth and it's lit reasonably, you'll be able to see it.
Thank you very much, Dave. Now, very, very quick one. Lord Gynoid, who's listening to us in Second Life, says, if your hair is red, why does it go white? Does it change structure? I don't think this is any different than if you've got dark hair. All you're doing is losing from the hair the ability to add some colour, which is what gives the hair either its red colour or its dark colour. It's forms of melanin, the same hormone, the same chemical in the skin that makes you go brown. You just lose the ability to add that to the hair, so you see the natural colour of the hair, the keratin, and that's the stuff which is white. Now, still to come on The Naked Scientist, we're going to be heading for Australia in a bit to find out how a didgeridoo does do what it does, if you see what I mean. But before then, it's time to find out what's been happening in the world of technology, as Mira Sinthalingam finds out about yet another polluter of the modern world.
Airlines often get a lot of criticism from the green movement for the amount of greenhouse gases they emit. But according to a new report, another industry could soon be overtaking them in this area. So I've come down to London to meet up with our resident tech expert, Chris Valence, to find out more. So Chris, what industry is causing all the problems?
It comes from a surprising quarter, this. These are data centres. These are the vast collections of computers that power everything from online banking to, well, let's say dancing hamsters if you watch those on the internet. They are these big computer warehouses that power the internet. Now, they do produce a lot of greenhouse gases. A report by McKinsey and Company suggests that by 2012 to 2015 they could overtake the airline industry in terms of the amount of greenhouse gases they produce.
But how do they produce so many emissions?
Well, the reason is they consume an awful lot of electricity. They consume an incredible amount of power. To find out where that energy goes and how they use it, I went to visit one data centre. Now, I can't say where it is, I can't say who it is, and I can't say who I spoke to, other than to say he was the person sort of in charge, and his name was John, and he took me on a tour of the data centre. Well, the room is filled with large cabinets, about the size of one of those really big fridges you might have at home. Each one is a rack of processing power. That computer processing generates a lot of heat. In fact, standing in front of this, I can actually feel the heat coming off the back. That heat has to be taken away, and if we come around the front, the floor, it's a little bit Marilyn Monroe. It's filled with air conditioning. There's cold air rushing up from beneath us to take that heat away. These computers, they obviously generate a lot of heat.
Typically, this industry, maybe 6-7 years ago, you'd look at your typical cabinet, would produce, I guess, 300 watts, maybe 400 watts of power, 3-4 light bulbs worth. You look at your modern blade servers, you can fit maybe 4 chassis into a computer cabinet, each taking 4 kilowatts. So you're looking at 16 kilowatts of power. That's 8 2-bar heaters for each cabinet.
And this room is filled with those cabinets. So that's a lot of heat. You can imagine this room being filled with 2-bar heaters.
Absolutely, Chris. So heat rejection is becoming a bigger and bigger problem in the industry.
So we're on the roof of the building, and in front of me, well, pretty much the entire roof space has been given over to air conditioning fans. John, I guess these are taking the heat away from those processes.
That's correct, Chris. We're looking at probably 2.5-3 megawatts of heat being rejected from this roof at the moment.
To give a sense of how much heat that is, if that were turned into electrical energy, that would be enough to power 1,000 homes.
Pretty much exactly right, yes.
3 megawatts of heat. And this is just going into space at the moment?
That's correct. It's just going into space.
That was an insight into the world of data centres, and it sounds like it's the amount of power they consume that's causing the problem.
It's the power needed to run those vast collections of computers, and then the power needed to cool them. I was told that for every watt that you have going into a data centre computer, it takes about 0.6 to 0.7 of a watt to actually cool that computer.
So is anything in progress to improve the situation?
Well, there are lots of efforts to try and make data centres more efficient. One of the ideas being proposed is that you could use the heat from data centres to do things like heat homes or heat swimming pools. The problem with that is data centres need to get rid of the most heat on hot days, which is, of course, when people least want heated swimming pools or heated homes. So perhaps there's only a limited use you can do with that. The main focus, to be honest, is upon making the data centres more efficient so that they actually just consume less power.
Well, if they're causing the problems, should we just stop going online to buy things then?
Well, far from it. Obviously, when we do online shopping or online banking, one thing we're not doing is driving our car to the shops or a car to the bank. So this activity of data centres, in a way, helps us save emissions. Perhaps they could cause less emissions than they do now, and that's the challenge.
It's all the Naked Scientist podcast that they're downloading. That's what's doing it. That was Chris Vallance, who is our tech expert in residence, explaining to Mira Senthalingam why the internet looks set to overtake aviation as leading producer of greenhouse gases.
And to put some numbers on that claim, the report mentioned by Chris actually found that data centres emit about 0.3 of the world's total carbon dioxide, which is a staggering...
0.3%.
0.3%, yes, well done, which is a staggering 170 million tonnes every year. And to put that into a bit of perspective, that's more than some entire countries release. For example, Argentina and the Netherlands both contribute less CO2 in total than data centres. That's amazing.
It's the Naked Scientist with Chris Smith, Kat Arney and with Dave Ansell. It's our science phone-in. If you'd like to get in touch, email chris@thenakedscientist.com. Alan's on the line. Hi, Alan.
Yes, hello there.
What can we do for you?
Well, first, can I congratulate you on your podcasts? They're brilliant.
Oh, thanks very much.
It's very good.
We're making the environment very warm, though, from these data centres. But apart from that, what can we do to help you now?
Right, it's a two-part question. First of all, when does a meteor or meteorite grow in size to become called an asteroid?
Well, asteroids are huge.
How small is an asteroid to become a meteor?
Okay, so that's sort of semantic. Meteors are things that are on collision course with something and then whizzing through towards them, and when they hit the ground, they become a meteorite because they're this congealed lump of rock which has melted on the way through and landed on the ground. So that's a meteorite. It's something that's made it to a planet's surface. Right. And an asteroid is this huge chunk of debris left in space, which is effectively a failed planet that never managed to form.
I understood that the meteors can be very large in tonnage.
Yes, they can, but of course an asteroid is something that's sitting there out in space as a failed planet, and when it's on a collision course with us, then you would mention that's a meteor.
Right. Now, the other thing is the impact craters that you get on Earth, how much would they differ on the Moon because of the lack of atmosphere, reduced gravity? Would a smaller meteor make a bigger crater?
Yeah, the same amount of energy will throw more material around, although of course a meteor hitting the moon will have, for the same size meteor hitting the moon will have less energy because the moon has less gravity. So for the same amount of energy you'll get a bigger crater on the moon, but the big effect on the moon is they're not getting eroded all the time by wind and weather.
Stripping down science.
Okay, let's do it.
The Naked Scientists.
It is The Naked Scientists with Chris Smith, Kat Arney, and with Dave Ansell. We also beam this programme into Second Life. Now, that's at 6 p.m. till 7 p.m. UK time, but that's 10 o'clock in the morning Second Life time, confusingly enough. So if you'd like to come and find our house in Second Life and meet some of the other people who are listening to The Naked Scientists, or at least you can meet their avatars, then you go to Second Life, go to the Scilands, S-C-I-L-A-N-D-S, Scilands, and look for The Naked Scientists Mansion, and you can relax on one of our wonderful sun loungers.
Lovely. And don't forget about this week's Kitchen Science. All you need to do is get a small bowl of milk, put a few drops of different coloured food colouring on each side, then drip some washing up liquid into the middle. If anything unusual or beautiful happens, let us know. On chris@thenakedscientist.com.
Thank you very much, Dave. Now it's that time of the month to catch up with what's been happening in the chemical world with Mark Peplow, who is the editor of the Chemistry World magazine from the Royal Society of Chemistry. Hello, Mark.
Hello, Chris.
Thank you for joining us. Now, what's all this about computers designing new ways to ward off mosquitoes?
Yeah, this is fantastic. DEET, the chemical compound DEET, is the gold standard in insect repellents, but University of Florida scientists have now trained a computer to come up with even better repellents. Basically, they took an artificial neural network, which is kind of a computer program that's trained to recognise patterns in huge, complex sets of data, and they let it loose on the US Department of Agriculture's database of insect repellents. 60 years worth of data, 40,000 chemical structures, and it slowly learned, with some help from the scientists, how to relate the structure of the compound, the position of atoms and so on, to its activity as an insect repellent. Then they gave it 2,000 new chemical structures, many of which had never actually been created, to have a look at, and it picked out 11 which of previously known molecules and 23 which were completely new and had to be synthesised. When the chemists actually made these molecules and tested them next to DEET, they found that they were much better. In some cases, they were active for 73 days as opposed to just about 17 and a half days.
Are they safe, these
DEET.
chemicals, Mark? Could they be applied to the skin safely without risk of harm to health?
Well, certainly the quickest way to try these things is to try them on your skin, and indeed the fearless chemists did try these out with little swabs, patches with this chemical absorbed, stuck onto their skin. Now, this is obviously a long way from being a new insect repellent going on the market, but they have identified the best 7 compounds which are now under further study.
Which is very exciting because mosquitoes are responsible for spreading so many diseases, and incidentally one of those chemists who tested it, I understand, is just having his other arm removed as we speak. Now, there's another interesting thing here about bubbles that can last for donkey's years.
Well, a year at least. Gas bubbles, they're incredibly important. They're an essential part of everything from ice cream, foams, paints, and the size of the bubbles really affects their properties. The trouble is that bubbles less than a micrometre in size, that's just a millionth of a metre, are really, really hard to make. The trouble is small bubbles tend to aggregate and merge into bigger ones. But now a group of scientists at Unilever, the people who make everything from paint to ice cream to washing powder and everything, teamed up with people from Harvard University, and they found a way to make microbubbles that last for longer than a year. Basically, they've used a particularly clever mix of surfactants. They're often used in detergents to keep oil and grease and water apart. These are molecules that kind of look like little tadpoles. They have a water-loving head and a sort of fat-loving tail. these tadpole molecules, they all line up in a big sphere and actually encapsulate and stabilise these micro bubbles.
So we mean better paints, better ice cream?
Well, exactly. The point is, if you think about... beer is a good example, actually. If you think about the difference in taste between, say, Guinness and a lager, a lot of that is actually to do with the feel of it on your tongue, whether you have really big fat bubbles in lager and tiny little micro bubbles in Guinness. So all of these things are very important for the chemists that make, like I said, everything from ice cream to paint.
Thank you, Mark. Now, lastly, superconductors, because this is really big business. We've heard about data centres consuming enormous amounts of energy and being very bad for the environment, but superconductors are a way potentially to alleviate that problem if we can find a way to make them work.
That's right. It's one of those challenges which is, I think, up there alongside, developing fusion power. Superconductors carry electricity with no resistance at all, and there are already many small-scale uses for them. But if you could actually use them on a very large scale, replacing cables in a power grid, you could transform the way we use energy. Resistance eats up about 10% of all the power that's pumped into the American power grid, for example. The trouble is, superconductivity only switches on at very low temperatures. About 20 years ago, scientists found some copper-based compounds, which are our best candidates for high-temperature superconductors. They start doing that at minus 135
But it's
degrees.
Still minus 135 degrees.
It's still pretty chilly. The trouble is, progress stalled at that stage, and no one knew how they work, and for a decade, nobody's really been able to improve much on that temperature. But now in the last 3 months, about half a dozen different groups in China and Japan have made really rapid progress with a completely different set of compounds. Instead of copper and oxygen atoms in these compounds, they have iron and arsenic, and there's a smattering of other elements which they've been tweaking, lanthanum, samarium, various other exotic things. And already in 3 months they've seen a 30-degree improvement in these compounds, which in the field is quite a significant improvement. Now that superconducting temperature, that threshold temperature, is still at minus 218 degrees, so it's a long way from being practical, but the key thing is it's revitalised a field where physicists have been banging their head against a wall for 10 years, making very little progress, frankly. And crucially now, these are probably the best alternative candidates that you can actually compare to. Like I said, nobody knows how these things really work. So if you've got one set of copper-based compounds, you can now compare them to these new iron compounds and try and work out how they're actually functioning.
Thank you very much, Mark. That's Mark Pepler. He's the editor of Chemistry World from the Royal Society of Chemistry, and you can hear other things from Mark and his team via their podcast, which is on their website at chemistryworld.org.
The Naked Scientists. For more information, get online at nakedscientists.com.
It's The Naked Scientists with Chris Smith, Kat Arney, and with Dave Ansell.
And now it's time to welcome the fabulously glamorous Diana O'Carroll back into the studio for this week's rather unglamorous question of the week. So, Diana, can you play the didgeridoo?
Well, thank you, Kat. That's a very nice introduction. Unfortunately, I don't think my lungs are quite big enough for such a very large instrument. But this week, we're going down under, and we're going to find the answer to the question.
Hi, this is Nick Lacey from Margaret River, Western Australia. My question of the week is about the acoustics of the didgeridoo. Could you please explain the science behind the cubic capacity of the internal chamber of the didgeridoo in relation to its length?
So what makes a didgeridoo when it has no reeds or finger holes?
I'm Neville Fletcher, and I come from the Australian National University, and over the past few years we've been doing a nice research project on the didgeridoo. It's the trunk of a small tree that's been hollowed out by termites, cleaned out, and somewhere between 1 and 1.5 metres long typically, and it can either be pretty much cylindrical or flaring a bit, just depending on the sort of tree it's cut from, and it's played by blowing in it very much as you would blow a trumpet or a trombone by vibrating your lips. And the longer the didgeridoo, the lower the note it will make. If it's about 1.5 metres long, it makes a drone which is about 2 octaves below middle C. That's about 65 vibrations per second. If it's cylindrical, if it's conical, so that it flares out at the far end, then it plays a higher note. And of course, if it's shorter, it also plays a higher note, rather like the fact that a trumpet plays a much higher note than a trombone, for instance. The main thing about the sound of a didgeridoo is you can change the actual sound quality In doing that, the player changes the shape of his mouth by moving his tongue, very much as you would if you're saying vowels. So you go I-I-O. In addition, the people have developed a technique called circular breathing, where you fill up your cheeks with air to keep the drone going, and then you quickly snatch a breath through your nose, and you can just keep the sound going for minutes and minutes at a time.
So the didgeridoo sound comes from a combination of length and shape. RD on our forum noted the similarity in physics with an organ pipe. But the most important factor is the technique used by its player. Using the right method, you could quite literally blow your audience away. So, branching out into the sea now, how is it that fish control their saltiness?
Hi, my name is Will Jimenez, and I'm calling from San Diego, California in the U.S. My question is, how do fish like salmon cope while being able to live parts of their life in both saltwater and freshwater?
And from the survival of the species to its engorgement, I'll be finding out how to kill the calories.
Hi, I'm Alan Wensky from Berkeley, California. And my question is one regarding pizza. Recently, a friend of mine was telling me about a pizza that he burned to the point of becoming a charred husk 10 times smaller than the original. At that point, I realized that this pizza had now become a very low-calorie alternative to its former self. This led me to wonder whether all types of cooking result in loss of calories as well. For instance, does a perfectly cooked egg or piece of toast also have less calories than the original?
If you know how to season your fish before adding lemon, or how to do a burned pizza diet, then get in touch by emailing questionoftheweek@thenakedscientist.com or join the discussion on our forum at thenakedscientist.com/forum.
Thank you very much, Diane O'Carroll, who puts together our Question of the Week each week.
You are listening to The Naked Scientist with Chris Smith, Kat Arney and Dave Ansell. We're getting close to the end of this week's show, and hopefully you're at home with a big bowl of multicoloured milk, waiting for Dave to let you know what should have happened. Dave, the milk, the food colouring, washing up liquid, show me.
Well, first of all, this experiment's all to do with something called surface tension, which is things water molecules are really attracted to other water molecules, but not to air. So if you have a droplet of water, the water molecules all try and stick together and make the surface as small as possible. And this kind of trying to shrink the surface is what we call surface tension. Okay, so I'm going to start off by I've got some milk in the bowl. I'm going to pour some food colouring into the bowl in 2 or 3 different places.
A couple of drops of red going in, a little splosh of green, and a little splosh of blue. So we've got like the milk, and then there's 3 pools of colour on the top.
That's right, and you'll notice that the food colouring is floating up to the surface because the milk's got lots of things dissolved in it, like calcium, which makes it denser than the water, so the food colouring will float on the surface.
Looks very pretty.
I'm going to get the washing up liquid and drip it in the centre.
Let's see. Woo! So like the colour's just kind of gone splosh and vanished outwards.
It's like everything's moved towards the outside, away from where the washing up liquid touched in the centre. That's because washing up liquid is a detergent or a surfactant, like Mark was talking about earlier. It's got a water-loving head and a water-hating tail. So it'll go up to the surface of the water, and so the water-loving heads will stick inside, so the water doesn't mind being on the surface anymore. The tails are sticking out into the air, and they're happy as well. So the surface tension gets much weaker. So where the washing up liquid touched in the centre, the surface tension is broken down, but everywhere else it's still really strong. So everywhere else shrinks because of all the surface tension. A bit like when you cut an elastic band, the elastic band will shrink either side where you cut it, so everything shrinks away to the sides, and that pulls lots of stuff to the outsides and then pushes the food colouring down underwater, and then it floats up again in the centre, making beautiful patterns.
I highly recommend that everyone tries this at home. It looks absolutely fantastic.
It's a stunning demonstration. Thank you very much, Dave. It really is worth it. There are some pictures of that on our website as well. You can find out more Kitchen Science on thenakedscientist.com/kitchen science. Right, we've got a question from Andrew. He's on the phone. Hello, Andrew.
Hello.
What can we do for you?
Why can birds touch electricity wires when we can't?
Oh, right, OK. Why they don't get electrocuted?
Yeah.
Well, actually, you could sit on an electricity wire and not get electrocuted as long as you didn't touch anything else. So the birds aren't doing anything special. The reason they're able to sit there is because they're not earthing or providing a route for the electricity to get from the wire down to the ground. Now, if you were to hang on the wire and touch the ground or the pylon that's holding the wire, then you'd have a problem, because the wire's at a very high voltage, the pylon is at a very low voltage, and you provide a very convenient circuit down to earth for the electricity. When the birds are sitting on the wire, there's no difference in their potential between one leg and the other, because both legs are sitting on the wire, so there's no reason for the electricity to want to flow through them, so it doesn't. Does that answer your question, Andrew?
Yeah.
Thank you for joining us on The Naked Scientist.
That's also the reason why you should never fly a kite near a pylon. Quick question for you, Chris. Do we bleed blue blood out of our veins? Presumably, this is a question from Steve Casimir. Presumably, if you bleed blood, it hits the oxygen and would turn red. Maybe if we bled in a vacuum, would it bleed blue?
The answer is definitely no, and I know this because I've done the experiment myself, because in hospital we use things called vacuotainers, which is a tube with a vacuum in the tube, and you put a needle into a patient's vein, you put the tube onto the needle, and this exposes the inside of the vein to the vacuum in the tube and draws the blood into the tube, and so momentarily the blood is exposed to a vacuum, and the blood comes out from veins very red. There's still too much oxygen in venous blood to make sure that it stays a red colour.
Why does it look blue?
It looks blue because when you have a bit of the tissue which doesn't have enough blood flow going through it, tissue will remove more oxygen from the blood, and it does mean eventually haemoglobin can get to be a blue colour. Normally that doesn't happen, but if you have an area of the body that doesn't have enough blood flow through it, then the tissue gets oxygen hungry and removes enough oxygen to make it go blue. Veins look blue as an optical illusion. They're not really blue, because if you cut through the skin, you'll see they're actually a sort of whitish pink colour.
Oh, lovely.
Sorry to disappoint, but that's the answer. You don't bleed blue, but I would like to try and do the experiment. Now, very briefly, Dave, why does a hot surface appear to shimmer in the distance?
Okay, when air is hot, it expands, and light will go through hot air slightly faster than cold air. When light moves from changes its speed at an angle, it will bend, like when it goes into glass or something. So you get lots of kind of turbulence with air moving up, which light will go through faster. So it will bend in all sorts of random directions, and this will change as the air moves, and you get this turbulence effect.
The same thing makes stars twinkle, doesn't it?
Yeah, you get turbulence up in the atmosphere, which bends the light coming from stars and makes them twinkle on and off. Sometimes it comes towards you, sometimes it goes away from you, and it gets brighter and darker.
Well, on that note, I'm afraid we have run out of time, so we'll just have to shimmer off into the sunset. Thank you very much, Fran, for that question. And thank you also to this week's guests, Chris Vallance, William Boynton and Mark Peplow, and of course our amazing production team here at The Naked Scientist, Diana O'Carroll, Ben Valsler, Miros Ethelingham and Petro Minch. Now, next week we're going to be solving the mystery of the real Ithaca, because what we call Ithaca today almost certainly isn't the Ithaca that's written about in the Odyssey, the ancient Greek text. So where actually is it, and did it even really exist? Well, now a team of classicists and scholars and archaeologists think they've actually found it, so join us next week to find out what they've found and what else they've uncovered. So that's bringing the stories of ancient Greece to life on The Naked Scientists next time. I'm Chris Smith, thank you for listening, goodbye.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.